it's recording. Perfect. Okay.
Okay.
All right. So welcome everyone again to the Set Theory Seminar. And Erin is going to continue with part 2 of her talk, the relationship between measurable and strongly compact cardinals. She's continuing from last time. Erin, go ahead.
Okay, thanks so much, Vika, and thanks to everyone for coming and for letting me give a talk here. Okay, I wanted to just go back a little bit. Let's see, so, sorry, just a second. To some of the slides that there were just a few missing slides that I want to show you just because I made them, so. But I also I just had a couple comments to make about Magador's identity crisis. Okay, and I have a couple of anecdotes at the end that are kind of related, but we'll save those for the end. Okay, so one of the things, just to be clear about what Magador showed, that he showed that you can have the first strongly compact be the first measurable, and you can have the first strongly compact be the first supercompact. And strongly compact implies measurable, and supercompact implies measurable, but you can't have the first measurable be the first supercompact. So just the identity crisis is that if you're, like, maybe you can think of it like if you're a strongly compact cardinal, yeah, you might want to be the first measurable in one universe, and you might want to be the first supercompact in another universe, but you can't do both in the same place. That's the identity crisis. And something I want to mention about this, these are directly, these are from Magador's paper. And does the consistency of strongly compact cardinals imply the consistency of supercompact cardinals? And this is still open. And I said this is solved by Magador. I'm just like mentioning that this is the way that he phrased it in the paper. What about the second, third strongly compact? Can it be the second, third measurable? And when I first read this, I still think so. That to me, I might be wrong about this. That he's maybe saying it can go up to omega or even higher when he's asking these questions. So to me, he's actually asking the open question of whether the first omega many strongly compacts can be the first omega many measurables. So I said solved here, but maybe we can think of it partially solved. Like he solved finitely many. We can have finitely many strongly compacts be the first finitely many measurables. So. Okay, I just want to mention that. And also, I was wondering if the outcome of this open question is positive, does it have any effect on this other question that's still open? That's just wondering about these things. Okay, and the other thing I want to show you, I showed you these the last time, is just a picture that I wanted to show you. Okay, so we talked about Mitchell rank and measurable cardinals. Okay, and I had this definition: an uncountable cardinal kappa is strongly compact if for any set S, every kappa complete filter on S can be extended to a kappa complete older filter on S. And I wanted to show you the picture that goes with that because I like that. Here's any set S, and kappa complete ultra filter can be extended to a kappa complete ultra filter. Okay, that's all I wanted to show you. And this definition that was missing last time also is just the definition of theta strongly compact. Just if anyone wanted to see it in writing, for any theta greater than kappa, if and only if there's an elementary embedding J from V to M with critical point kappa such for all T subsets of M, where V thinks that T is size less than or equal to theta, there's an S and M that contains T such that M thinks that the S is size less than J of kappa. And equivalently for strongly measurable cardinals, there's a kappa complete fine measure on P kappa theta. So I mean, we're talking about the relationship between measurable and strongly compact cardinals, and and this is true about a lot of large cardinals. The strongly compact cardinals are themselves about an embedding and a relationship between M and V and how they see things. Okay, and we had a lot of comments on this slide last time, and I really appreciated all the comments and the anecdotes and slides last time. My brain sort of panicked and I thought they're gonna kick you out of set theory or something, but everything was fine. So I just we might come back to this too. I'm just kind of mentioning some things that if there's time at the end, we can come back. This slide had a lot of good comments, and I think Gabe asked a nice question that maybe we can answer or partially answer. And I think this is true that Arthur's mentioned that something else is interesting, that Magador actually proved this theorem first, that the first strongly compact can be the first supercompact. And so maybe the proof of that isn't as like height that you might want to be. This is just proof. And then he did the measurable and strongly compact second. So just to mention, if we want to come back to that later. Okay, so we can get started now then. Kind of like, it's gonna some noise, but okay. So the theorems we're using is Magador's prick reiteration, and that's an iteration of prick reforcing with finite support in the stems and full support in the measure one sets. And prick reforcing is all about changing the cofinality of a cardinal, and this is what this the stem is. It's like going to create the new cofinality. And then we also have Magador's non-reflecting stationary set iteration, and this was as presented in after Cummings' paper, adding a non-reflecting stationary set of ordinals of some fixed small relative to kappa cofinality to measurables below kappa. And we're going to be adding iteratively with Easton support. Okay, so we can see which forcings we use in which theorems, and maybe sometimes we can use either one. But these are the main. Okay, so the main theorems, we're going to go through each of these, and that's what the talk today is about. But I wanted to mention something about universes here. So there's a universe where kappa is the least strongly compact and has Mitchell rank 2, and it's the least of this degree. And I since there was a good question last time about universes and what's a universe, I just wanted to mention that for me, a universe is a model of ZFC. But often I like to, when I'm forcing, I like to be in a place that has GCH. So sometimes I'll say force the GCH if necessary, like as if you don't already have it. And also, I like to be in a place that has some supercompact cardinals or strongly compact or measurable. So just mentioning what to me is universe. And the multiverse is like, this is basically a direct quote from Joel, but the multiverse is a vast place, and there's places that you might not want to go, like a place that has not con ZFC, for example. So there might be some preference in the multiverse where you'd want to be. And I'm saying out in universes with some large cardinals. I like the GCH for for forcing. But also just to mention, like large cardinals themselves, I think are a universe because it's a place where you can do mathematics. Okay, so just to answer that nice question. The second question, second theorem we'll have is for any increasing class of measurables, there's a forcing extension where kappa I is the I measurable cardinal for I in I. And so when I asked people what, show people this theorem, set theories have different opinions about how we can do this. Also, I want to mention like a universe, like the constructible universe L is also like a nice place. I don't know that much about intermodal theory though. But yeah, there's lots of ways to prove this, but maybe we should try and think. I think someone's like not muted, maybe. Okay.
I'm hearing a lot of noise, so can everybody other than the speaker mute themselves? I think that would help. Thanks.
Sorry, it's just
yeah, I was hearing it also.
Okay. So for this one though, but wouldn't it be great if we could do this even in a more careful way than maybe we have done so far, because maybe this isn't the path to go down to solve the open question, but if we could like take a class of strongly compacts and make them the first however many measurables. Obviously we don't have the forcing to do that yet, or you could solve the open problem. So for this question, there are a lot of ways to do this, but let's try to improve and get do it in the most gentle way possible. That's what I have in mind. I don't know if that's what we did, but that's just to comment on that theorem itself. Okay. And then there's a universe, then we get into these kind of ascending and descending cases where we have the first and second strongly compact cardinals, and maybe the first one is Mitchell rank 2, and the one above that is the least measurable above it or something. Or it turns out we have this ascending case, which is actually harder, and that's where the first measurable has Mitchell rank is the least measurable. The first strongly compact is the least measurable, and the second strongly compact is the least of Mitchell degree 2. And then, so we have this last theorem here that we're going to talk about is the descending case. For any finite level, we can have the like 17th strongly compact be Mitchell rank 18, the 16th strongly compact be Mitchell rank 17, and so on. But we don't have this for the ascending case. Okay, so this is just for the names of the theorems, and it's just, again, not to do with the proofs or anything, but just imagine a world where you could have a straight in one direction, but maybe not a straight in the other direction, or that they had different probabilities. Because that's really what's going on here, is that we in these theorems, we'll see that these two theorems seem pretty similar, but one we can do and one we can't do. So so you can imagine maybe, okay, and just again, this is just for the names of the theorems, but the real value of these cards starts with ace of clubs, I believe, and then goes down like this. But just because of the way the picture is, that's just for why I named things the way I did. I think of this as like, this is like 1, 2. This is like 3, 4. It's like all the cardinals here, and then we can have more. I don't know, king, emperor, the sky, the moon. I don't know. So it can go on forever, maybe. Okay, so let's start with the ace of spades, Magador's theorem. This is what Magador showed in his paper. Just going to putting it in with the theme of the rest of these theorems. And there exists a universe where kappa is the least strongly compact cardinal, and it has order of kappa 1 and is least of this degree. Okay, and we can just do what Magador did, his a prick reiteration to kill all the measurables below. Okay. So that's the ace of spades. So it's like we always had this up our sleeve the whole time. The ace of hearts. Okay, so there's a universe where kappa is the least strongly compact and has Mitchell rank 2 and is least of this degree. Okay, and you can see in the proof that this can be generalized. O of kappa could be any finite number, and this proof would work fine. Okay, so we're going to start a universe with a supercompact cardinal. Okay, and so I wanted to mention, like, you could be more careful about how you state these theorems, like I did in my thesis. Like, sorry, just gonna mention how maybe it should be. But
Erin?
Yes, Arthur.
Yeah. So O of kappa can be anything. It doesn't have to be a finite number.
Oh, even
You said it could be omega. It can be anything up through, if you assume GCH, up through kappa double plus. So there's no restriction if
right,
you're talking about the least strongly compact being the least of whatever. It can be of any Mitchell rank.
Okay, great. Thank you, Arthur. And that's just like what I did in my thesis, which was that you can, except in my thesis, I wasn't trying to preserve strong compactness, but I just want to mention, like, you could say for any V, a model of Z of C plus GCH and any ordinal alpha, there's a forcing extension V of G where every cardinal kappa above alpha in V of G has this Mitchell rank that you like. But I just sort of put the GCH not in the statement of the theorem, but down here. And also, like, having a supercompact cardinal, you could put that as part of the, like, hypothesis for the theorem. Okay.
Can you start with a strongly compact of Mitchell order 2?
I'm not sure if what
Yes.
degree
Yes.
we can have for the supercompact cardinal.
You can start for this theorem, the theorem that's on the slide. You can start with a strongly compact of Mitchell order 2. Yep.
Oh, instead of a supercompact cardinal.
That's right.
Oh, that's interesting. Okay. Okay, so we're going to force the GCH if necessary, if we don't already have it, and start in a small universe with no order of delta 2 for delta greater than kappa. So we'll use an Easton support iteration, adding non-reflecting stationary sets of cofinality omega to each delta less than kappa with order of delta 2. Okay, so this is going to kill the strong compactness. The strongly compacts below, I believe. By my thesis, these arguments, this is like Joel's arguments about approximation and cover properties. This is like it's like a very gentle lifting argument. But that's all written out nicely somewhere. And kappa is least with order of kappas 2. Oh, this is also part of the Solovay-Reinhardt-Kanamori result, theorem 4.8, that that there's no strongly compact cardinals below. So by Magador's unpublished result, which was published eventually by Apter and Cummings, kappa remains strongly compact and there's no strongly compact cardinals below kappa. Okay, and so, and yeah, maybe we can even make this, relax this a little bit. Any other questions or comments so far? Okay, so that's the first one. We can make, so we can make Mitchell
Can I
rank.
just make a quick comment? The
Sure.
quick comment is that with this proof, if you're starting with, as Gabe asked, for a strongly compact with O of kappa equals 2, with the proof you're giving, you may have to assume GCH in addition. So what I'm saying is with a supercompact, it doesn't matter. You can just force the GCH and you're fine. But if you're starting to weaken hypotheses and give this non-reflecting stationary set iteration proof, you may need to assume GCH or 2 to the kappa equals kappa plus, something like that. That's
strongly compact is known to be equiconsistent with strongly compact plus GCH, right? I'm not asking about Mitchell order 2.
Okay,
I'm not saying that I know that, I'm asking.
No, I don't know that at all. Strongly compact being equiconsistent with strongly compact but GC plus GCH, as far as I know, that's completely open.
Really?
Yeah, I don't, as far as I know, that's completely open. Now, of course, Gabe, if you have, if you have the ultra power axiom, then I guess it would change things. But if you're not assuming that,
consistent then.
If you're not assuming that, it's not known. It's completely open.
Okay, thank you. Or does anyone?
Erin, 1 second. So it's not known that you can somehow do the GCH forcing and preserve strong compacts?
Not known at all.
Okay, I did not realize that. I see. Thanks.
So you're saying if you did start with a strongly compact with order of kappa 2 to do the proof, you might have to already be somewhere where GCH holds. You might kill strong compactness or something.
That's right. I think if you're doing the proof with the iteration of non-reflecting stationary sets, then you need some amount of GCH. But if you're doing it with a Magidor iteration of prick forcing, then I think you're good. I don't think you're going to need any GCH assumption. So it just depends how you're doing the proof, I think.
Okay, and we talked a little bit about how maybe you could do the proof with prick reiteration, but maybe we'd have to do something different, or I can't remember exactly. That was just something we were talking about.
Well, your talk is talking about research that's still in progress. So I think the upshot of the conversations that we've been having is that we absolutely believe that we can do it with a prick reiteration and preserve the fact that O of kappa equals 2, but we haven't written down all of the details yet. I don't think there's any problem with that, but if you, strictly speaking, want to say what the current state of knowledge is, we're still working on it, but we don't believe there's any problem with it. I think actually there's a recent preprint, recent from last June of Gittick, and I can't remember the name of his co-author. And I think he uses something like that, but he's not talking about Magidor iterations of prickly forcing, maybe non-stationary support iterations, but I'd have to check the preprint again.
Okay. Well, thank you.
Um,
Yeah. Mhm.
So in this argument, you're essentially destroying the measurables of order 2 below kappa. What happens to the others, the measurables of order 1? Do they survive, or do some of them undergo collateral damage?
Well, I think that they survive. I mean, at least in the forcing that I did in my thesis when we added clubs, like there's no measurables. Oh wait, those measurables were yeah, no, you can lose your rank, but you're not your measurability. So I think they all survive. The measure 1, but I could be wrong.
I think you may need to have with this, I think you may need some GCH assumptions here, because what I'm worried about is that if you're doing this non-stationary, if you're doing this iteration of non-reflecting stationary sets, or as Erin does in her thesis, adding clubs of non-measurables, whatever, and you come up to a measurable limit of measurables, or a measurable limit of measurables, let's say, and you want to try to lift the embedding, I'm a little bit worried if you don't know that for that delta, that if 2 to the delta is greater than delta plus, I'm afraid that the lifting argument might not work. So I think that the answer to that question, Andreas, is that you may need some assumption of GCH. If you have GCH, I don't think there's any problem whatsoever. If you don't have GCH and you're doing an iteration of non-reflecting stationary sets or clubs shooting whatever, then I'm worried if you don't have GCH. Prickly iteration, I don't think there's a problem though.
Thank you.
Yeah, and thank you, Arthur. And I agree with Arthur on that you need GCH, I think, to preserve measurability. Okay, thank you for all the good questions on that. Okay, this is the collapse straight, the one we had to talk about a little bit. Collapse straight. So basically, for any increasing class of measurables, we can make them the first however many measurables you like. And like I said, a lot of set theorists might have different opinions. And last time people were talking about maybe inner models where you can make this true. And but whatever our methods are, maybe they aren't good enough, because if they were really good at preserving, if this theorem was really good at, it's really good at destruction, but if it was really good at preservation, then we could maybe preserve strongly compact cardinals. So, but this is what this is basically how you can do it, and what we have for now. But this theorem could be really awesome, right? Or really important if we could preserve a lot while doing it. Okay, so for any increasing class of measurables, kappa, alpha, alpha, and I, there's a forcing extension where kappa I is the ith measurable cardinal for I and I. So we're going to use Magador's iteration of prickly forcing, which kills all the measurables which aren't a kappa I cardinal. I said this is the first omega many, but that's for, I'll just say however many. And P does not create new measurable cardinals. So maybe a theorem that everybody knows or something, but can we do it?
Once again, no GCH assumption required here. Power sets can be anything you want. You don't need GCH.
Okay. So that's good. So we can, so this is yeah, okay, we don't need the GCH to do this. Maybe if we had the GCH, we could preserve more or something, or if we wanted to be more careful. I don't know. Okay. So this is the descending pair. And there's a universe where kappa 1 and kappa 2 are the first and second strongly compact cardinals, respectively, and where O of kappa 1 is 2 and is the least of this degree, and where O of kappa 2 is 1 and kappa 2 is the least of this degree above kappa 1, and there's no order of delta 2 between kappa 1 and kappa 2, Or in other words, kappa 2 is the least measurable above kappa 1. So we're going to start in a short universe, and I'm just going to draw the picture here. Order of kappa 1 is 2. Order of kappa 2 is 1, and there's no measurables in between here. So start in a short universe. Okay, we need a short universe where kappa 1 and kappa 2 are super compact with no measurables above kappa 2. Okay, and so kappa 1 and kappa 2 will become our strongly compacts here with the desired Mitchell rank. So force if necessary to a universe where V models GCH, and if you would like to be less restrictive on that, we only need GCH at kappa 1 and kappa 2. We are going to make kappa 1 indestructible, and it's a small forcing, so kappa 2 remains super compact. We didn't do anything to affect that. So first force with P1, which adds cardinals delta between kappa 1 and kappa 2, order of delta greater than or equal to 2, a non-reflecting stationary set of cofinality kappa 1. So that's P1 is to these cardinals here. Then force with P2, add cardinals to gamma less than kappa 1 with order of gamma greater than or equal to 2, a non-reflecting stationary set of cofinality omega. So this is. Okay. And then let's go. So let's see if I can. So the order of kappa 1 is 2, order of kappa 2 is 1, and we have first force with P1 and then force with P2. Okay, remind myself even. So for P1, we're adding non-reflecting stationary sets of cofinality kappa 1, and P2 is non-reflecting stationary sets of cofinality omega, and this is to all the order delta 2. Okay. By Magador's argument, kappa 2 is least measurable and strongly compact above kappa 1. We kill all the old order of delta 2 below kappa 1 with P2. It's a small forcing, so kappa 2 remains the least measurable and strongly compact above kappa 1. There's no strongly compacts below kappa 1 by this theorem of Solovay, Reinhardt, and Kanamori, theorem 4.8. Kappa 1 equals 2 and is least of this degree because of approximation and cover properties in the thesis. So we're lifting and embedding. We're actually lifting 2 embeddings. And kappa 1 is the least strongly compact by Magador's argument. And it actually has strong compactness up to kappa 2, and kappa 2 has no measurables above it. So this is the real reason. Okay. So any questions about that one before I go to the next one? Okay. So this is their proofs are actually pretty similar, but this is a very shortened down version of the last proof. But they are kind of similar. So this is the ascending pair. So there's a universe where kappa 1 and kappa 2 are the first and second strongly compact cardinals respectively, where order of kappa 1, I don't know, you might think this seems more natural, or at least I felt like it was, but it's maybe the more difficult case in the long run. So we're going to start in a short universe, no measurables above kappa 2, where kappa 1 and kappa 2 are super compact. Okay, again, we're going to turn these into the strongly compacts with the desired Mitchell rank. So force the GCH at kappa 1 and kappa 2, and also force the indestructibility of kappa 1. Add a non-reflecting stationary set of cofinality kappa 1 to order of delta greater than or equal to between kappa 1 and kappa 2. So that's killing all of the, that's making kappa 2 the least of Mitchell rank 2. Then force with Magador's iteration of prick reforcing to make kappa 1 the least strongly compact and the least measurable. So it's kind of a combination of Magador's two theorems, in a way, or using that forcings. Okay, so the reverse straight flush, aka the descending case. Okay, so we call this the descending case because as we go up, it's descending. Maybe that's clear. And so we can do this for any finite number. So we can go, like I said, we can go 17, 16, 15, 14, 13. I think I said it earlier when I was describing this. I think I said it wrong. I'm sorry. I was describing it the ascending case, but okay. Okay, my numerology is wrong. So kappa 1 can be any finite number you like, 17, and then the next one will be Mitchell rank 16, the least above that of Mitchell rank 16, and so on. So we're just gonna the proof here is just gonna be for this case with 3 cardinals, the first, second, and third the least strongly compact, and then you can see how you can generalize it. Okay, so this is one where order of kappa 1 is going to end up being 3. Order of kappa 2 is going to end up being Mitchell rank 2, least above kappa 1 of this rank, and order of kappa 3 is going to be Mitchell rank 1, and it's the least measurable above kappa 2. So we'll start in a short universe. No measurables above kappa 3, where kappa 1, kappa 2, and kappa 3 are super compact. If needed, we'll force the GCH, or maybe we had it to start, at least at kappa 1, kappa 2, and kappa 3. And force kappa 1 and kappa 2 to be indestructible. Next, force with P1 adding non-reflecting stationary set of cofinality kappa 2 to delta measurable between kappa 2 and kappa 3. Trying to make kappa 3 the least measurable above kappa 2. Then force with P2 adding non-reflecting stationary set of cofinality kappa 1 to order of delta 2 between kappa 1 and kappa 2. And then finally, force with P3 adding a non-reflecting stationary set of cofinality omega to order delta 3 below kappa 1. Okay, and you can see how it kind of works, because here I'm just killing, with P1, I'm just killing measurables in between here, and then with P2, I'm killing Mitchell rank 2s, and then I'm killing Mitchell rank 3s below here. Okay. So I'll go on, but if I can come back if anyone has a question. Okay, so this is actually the last theorem with the proof outline. And I'll talk about why the ascending case, why that doesn't work so far with what we have so far. Here's an open question. I'm calling this the full house. Are there universes where the first n many strongly compact cardinals are the first n many with order of delta with Mitchell rank k for any k and any n? So I want to have the first 5 many strongly compacts have Mitchell rank 7 and be the first 5 of this Mitchell rank. Does that make sense? Something like this. Okay, so far we don't have.
So, Erin, can I Can I ask, so, I mean, can you do special cases of this question? I mean, it seems like Magador did what when K is 1, I guess,
Yeah.
is Magador's theorem. And then for 2, is it already hard?
Okay, so if we made if we made K equal 2, well, I guess if K equal 2 and N1 is the ace of hearts, I guess. But okay, so you're just saying, I don't know, like if we just had the first 2 be Mitchell rank 3 or something, is that hard?
Either or. I mean, and maybe the first, I don't know, maybe the first 2 strongly compacts are the first measurables of Mitchell rank 2 or something. I don't know. I mean,
Yeah. So far,
I'm just asking, are there easy cases, or are the easy cases just what Magador did?
I mean, as far as I know, but maybe other people can comment. I think that even this is
Okay,
but I don't
so
know.
for n equals 2, Miha, it's we can do it. So whatever you want, if you have the first 2, the orders can be anything you want. There's no problem. So you can have ascending, descending. It just does not matter. We can do that. I mean, again, there are still a few details to be checked, but I don't think there's any problem. I'm just about like 99.99% certain that we can just claim it as a theorem that for n equals 2, that you can have the first one have order 75, the second one have order 928, or order omega plus 74, whatever. You can just have whatever you want, but it's when you get beyond 2, when you get to 3, that there are problems that we have no idea how to do. But 2, it's completely, we can do it completely.
What about 3 when one of the steps is easy, but maybe have an ascending and a descending in one order or the other? Could you do 3 like that?
Well,
so you mean the first one is, let's say the least one is the least measurable, the second one is the least of order 2, and then the one above that has order 1, let's say.
Order 1, it is the next order 1.
Yeah, actually, I think you can do that. I think you could actually do that, but maybe not get beyond that. So I think that that's actually possible. I mean,
Yes.
again, I don't want to claim it as a theorem, but it seems to me as though it would be. It seems to me as though it would work.
Yeah, Arthur, as long as the third one is the smallest, I think you're fine, right? It doesn't matter what the numbers actually are.
Right, but I think also that the third one, you could have the if you want to do it for 3, I think you could do it for what we were calling the descending case. So you could have the first one, whatever you want. The second one is then whatever you want. And then the third one is just a lower order that that's what we would mean for the descending case. I think that's fine. I think that would actually work.
Right, as long as the third one is at least as small as the first, right?
The third one, no, the third one should be smaller, I think.
Yeah, smaller
than the second.
Smaller than the second, okay.
Yeah.
The first one, it's not going to matter.
Right.
Because of this short universe above. That's usually where the third, if the third one's higher, that's where we get into problems, is because we need like a short universe above the second one, and we can't have that if we need the third one to be a higher order. Okay, thanks, Miha. That's a good question. We can talk about that some.
Yes, and also thank you, Andreas, for that question, because that.
Oh, thank you, Andres.
And thanks for good answers.
Well, I mean, that question, Andreas, I think that we now know we can do more than we knew before this lecture began. So thank you. That was really good question. Thanks.
Maybe we could write like what sequences are possible or something.
Right.
Okay, great. Okay, and this is the open. This is what we're just talking about. If kappa 1, kappa 2, and kappa 3 are the first supercompact cardinals, there's a forcing extension where kappa I is the least strongly compact cardinal, and with least with O of kappa I is I. And so far, we cannot generalize the proof of the ascending pair for the ascending triple because we needed a short universe in that proof. And we can't iterate prickly forcing above a strongly compact cardinal without killing the strong compactness below, without killing the strongly compact cardinal that you just went above.
Which is why what Andreas was asking, we can't really, I don't think we could really get beyond 3 because for 2 of them, we don't need to do a prick reiteration. So what we could do is for the first one, we have a prick reiteration, and then above that, we have 2 Easton support iterations of the appropriate cofinality of non-reflecting stationary sets. But if you wanted to get it for 4, then we're running into the problems that Erin was just saying, where if you want to, well, okay, I guess. Well, let me back up on that. I guess what you, well, I guess this still requires thoughts. I mean, I'm now just blathering on. I think that I would need to think about it a little bit more. But I think we can only do for we could do for n equals 3 that mixture that Andreas was saying, and I think beyond that we're going to have problems. We'd have to go into the descending case. We couldn't have the arbitrary mixtures, but whatever.
Okay. Yeah, there's still a lot to think about that we're still working on. So thank you. Okay, this is open. It's just the omega version of the last one, the ascending case, or it's like Magador's. It's like Magador's question, but with Mitchell rank instead. So maybe we can solve these. I don't know. Okay, so there'll probably be some time for questions. I'll just go. I have a little anecdote at the end, but so some of the references. I'm sure there's some more. Magador's paper, of course, and this Solvay Reinhardt Kanamori theorem 8, 4.8 is this one where the least where we have like here. I shouldn't even brought it up. Where we have no strongly compact below kappa 1 because of this theorem. SRK is what this is from. Okay, and so thanks for, okay, so I had a little anecdote because I work at a wine shop on the weekends, and I was, most of the time I really like it, but most of the time is just passing the time with my coworker and thankfully he likes to talk about set theory. He's an artist, and he said, after we were talking for a while, he said, how do you know if you're in a forcing extension or not? How do a universe know if it's in a forcing extension? But I said that's like set theoretic geology, so Jonas might have to ask him, but anyway, I told Fred Galvin that I worked in a wine shop, and this is his nice response. But he's Fred Galvin's a set theorist. Well, he says he's not a set theorist. But it's kind of like part of the identity crisis. I think he is a set theorist. But anyway, this is the anecdote from Fred Galvin. He said, "You're working in a wine store reminds me that 50 years ago when I was at UCLA and still single, it was a daydream of mine that someday I'd be out of academia and owning my own beer and wine joint." I can relate. Not a bottle shop, but a drinking establishment like the one I used to hang out in Berkeley with candles and wine bottles and blues and folk music on tape. And just, so maybe we all have this identity crisis sometimes. So thanks, everyone. Thanks so much. And
Thanks, Erin. I like your ending very much.
Yes.
yeah,
Okay,
like,
we already had a lot of questions, but are there any more questions for Erin?
Just going back to the strongly compact and GCH question, is it known you can force 2 to the kappa is kappa plus? Like just collapse some singular strong limit above with large cofinality to kappa or something? After doing like the Usuba thing.
To the best of my knowledge, if you're just working with a strongly compact, nothing like that is known. I think that the best result that I know of, maybe along those lines, is this result due to Usuba, who showed that you can start with a strongly compact and then forced to make the strongly compact indestructible under adding as many Cohen sets as you want. So you don't need any assumption of supercompactness. You can just do it from strong compactness.
Right, but does that not work to allow you to collapse to kappa, however high you like?
I'd have to look at Usuba's proof again, but my guess is that it does not. I don't think it does, but I'm not sure.
Okay, thanks.
I mean, it seems to only allow you to blow up
Right.
the kappa, right? Not
Well, I mean, I thought it was like the conditions were small, but okay. Maybe it won't work. Probably.
Arthur, was that the result you promised to give a talk on at some point that everyone was super interested in and wanted to know the proof of?
Well, maybe at some point, but at my age, I can resist crowd pressure. So maybe it'll happen at some point, but we'll see. My fellow senior people here, I think know what I mean about resisting crowd pressure. So.
But I'm just saying that if ever you decide that you have some time, this is something that I think a lot of us would love to hear. I mean, I'm super interested, friends.
Yeah, it would help me learn the argument better also, I think.
and
That side note.
we also there. Do you want to talk about Gabe's question from the other slide, Arthur, or?
Yeah, I can say something about Gabe's earlier question, but also again with Andreas's question from before. So I think what you can do, Andreas, for and everybody else, for three of them, that the first two, and also getting back to Miha's question, for the first two, they can be whatever you want, but you can do the third one has to be descending, less than or equal to in terms of order. I think that's what's going to work, but I don't think you can push that beyond 3. I think for 4, it's probably not going to work because you're going to have to do a prick reiteration, which you can't do. That's at least my feeling at the moment, but I'd have to think about it more. But anyway, so Gabe's question from last week. So this was the question, Gabe, when we were talking about the we were talking about modifying Magidor's proof, and I said using strong cardinals, which aren't limits of strong cardinals, and you made the suggestion, well, what about using cardinals such that nothing is super compact up to them? And I said, oh yes, I think you can do that. And I think I need to expand upon that answer a little bit that I gave, because I've been thinking about that some more, including, by the way, at 3 this morning when I was having my usual insomnia and awake, and I realized that there was still something else to say about it. But anyway, so with the strongs that aren't limits of strongs, when you kill those, you can, it doesn't matter if you're working with the least super compact cardinal. It can be any super compact that you want. But if you want to try killing things such that nothing is super compact up to them, you better be working below the least super compact cardinal. That's the first thing, because then if you have a super compact, you have something that's super compact up to everything. So that's the first remark. The second remark is that even if you're working below the least super compact, you can't just say measurables or whatever you want such that nothing is super compact up to them, because that would be all the strong cardinals, and you can't just kill all of the strong cardinals below and preserve super compactness. So that's another remark to make. Still, a third remark to make about this is that now if you look at, so you want to do what you were saying, Gabe, and you want to look at things such that nothing is super compact up to them. If you want to do that, with non-reflecting stationary sets, I think you can do it, but you have to say non-measurables such that nothing is super compact up to them. So, and that's fine, but there's still a little bit of a wrinkle with that as well, I think, because I think that if you're doing that, you're not doing a prickly iteration, because you're talking about adding non-reflecting stationary sets to non-measurables. So what I'm a little bit worried about, but I don't think it's a problem. If you have GCH, I don't think there's a problem. But suppose you don't have GCH. Well, but in actuality, because you have a super compact and hence a strongly compact, you have a proper class of cardinals above that kappa. The kappa is going to be the least one that satisfy GCH by Solovay's theorem. So I think what you would need to do is you'd need to pick some lambda bigger than kappa, which is a singular strong limit cardinal of cofinality greater than or equal to kappa. Maybe for safety's sake, let's say greater than kappa, I think. So pick that and take, and if so, let's call that lambda, and take an embedding J from V to M such that kappa is not lambda super compact. So now we want to lift that embedding. Okay, well, so we're not going to do any forcing between kappa and lambda, not at kappa, because we're working with non-measurables, and then kappa is super compact up to everything. So we're not going to worry about that. So what's going to happen is, I think the first place at which we would do a forcing would be at lambda plus. So the successor of this big singular strong limit cardinal, this cardinal of cofinality, let's say at least kappa plus. Okay, and I think that we're going to be fine here, because the remainder of the iteration is going to have cardinality J, J of kappa, and we have to look at that. How big is J of kappa? Well, let's see. So we're looking at functions from p kappa lambda into kappa to get an estimate of that size, or to get what that size is. Lambda to the less than kappa is going to be lambda because it has big cofinality, and then because of Solovey's theorem GCH, so kappa to the lambda is the same thing as lambda to the lambda, which is lambda plus. So I think we have the numerology correct, that we can now just, and there are only so many, I guess, whatever, lambda many, because it's an Easton support iteration, it's lambda CC. So I think there are only lambda many maximal antichains that you have to meet. And so I think you can just meet all of them. So what I'm saying is, I mean, I think what I just said is okay. If I'm missing anything there, I'd have to think about it again. But I think what I said should work. But the answer to your question that you asked last week, the answer to Gabe's question, you need to, you can't just blithely say, oh yes. I think there are some additional things that you need to look at.
So I have to leave right now, but I thought we were saying you perk force at the Mitchell order 0 measurables that have nothing super compact up to them. I thought that would work.
Okay.
But I have to leave right now. I have office hours. So bye. Thanks.
Okay. Maybe I misunderstood the question. Sorry, or misremembered it.
But still, Arthur, maybe you're the first person to have proved the theorem on Zoom.
Whatever, who knows? But the way things have been going over this last year, probably there have been other people who've been rambling on about theorems on Zoom seminars and have come up with things.
Possible.
Yeah, but you do have an amazing ability to talk math without having to write anything down. I cannot do that for the life of me. I cannot keep track.
Yeah, the oral mathematic tradition. It's a new thing, Arthur. Launch it.
Right.
But oh, sorry, Arthur, go ahead.
No, I was just going to say, Gabe has just left. If what he was saying was Mitchell order 0, do a prickly forcing at cardinals of Mitchell order 0, so that nothing is super compact up to them. That, if you're working below the least super compact, again, initially that strikes me as though that's going to work. I'd have to think about it, but that strikes me as though that's probably going to work, I think. But it requires some more thought. And if it does work, it's not going to require any use of GCH. Okay, go ahead, Ken.
Oh yeah, I just want to order sort of let's call an anecdote about cafes and mathematics. Before World War II, there was a great center of Polish mathematics was at the university at Lvov, but that city is now in Ukraine and it's called Lviv. But the professors at Lvov included Banach and Steinhaus, and that's where the Scottish book was kept in his cafe. And Banach had the legend that of all of them, he could both drink and do mathematics. And he's apparently the best in history at doing the two at the same time.
I see. There's no identity crisis there.
But now they moved the Scottish book to Wrocław, which used to be Breslau.
Any more comments, questions before I turn off the recording?
No, this is great stuff. Thanks, guys.
Thanks so much, and thanks everyone. Thanks for all your great
Yeah,
comments.
thank you.
And Ken,
Thanks, Thanks.
Ken, it's good to see you after all these years. I'm glad you're here again.
Likewise, Arthur.
Are you in Paris? Where are you now?
No, I'm on Old Cape Cod.
Oh, okay.
Watching sunsets.
Okay.
Yes.
Great. Thanks, Erin. I'm going to turn off the recording.
Okay, yeah, thanks Vika. Thanks everyone.
I just wanted to